Our first lecture in BY 245 is going to be focused on answering the question, what is science? Much like life itself, science defies simple description. It is often thought of as a collection of facts. However, it's also the process of obtaining facts. As a body, science is often seen as a thick textbook filled with facts. I'm sure you've seen one of these before, maybe your BY 123 and 124 textbook. But science is also the process of how those facts are obtained. At its core, science is concerned with developing an increasingly accurate understanding of the world around us by using observation and reasoning. And the way that we conduct observations and reasoning is through what we call empirical measurements. These empirical measurements can be broken down into what we call quantitative or qualitative measures. Quantitative measures are those that have a unit of measure. Qualitative measures require scaling or other numerical manipulation, if you will. Now, these types of measurements will come up later in the semester, so we'll come back to that. I just wanted to introduce you to the terminology. We're now going to watch another video called The Nature of Science. Pay attention because there's some really great information in this video.
Let's say if we have this many of something, we'll call it 1 and represent it with this symbol. If we have this many, we'll call it 2 and use this symbol. If there's none, if there's a certain amount of something and that amount is none many, we'll call it 0 and use this symbol. This many, call it 3, da-da-da-da-da. If there's this many, we'll call it 10, and we're all out of symbols. So we'll just start reusing symbols, and so on. This is a way we can represent quantities with words and symbols. And we can represent lots of properties with words, like redness. They can have shapes. Things can be cold, scattered, or patterned. They can be wooden or wet. Even though two things are shaped differently and are made of different materials, we may still call them by the same name because of other characteristics. Things can have movements or behaviors, and we can have descriptions that only come when we're comparing or looking at multiple things. Any characteristic, property, or concept that we can think about something, we always also have a word for it. I think. That might not be right. You. Try to think of something that exists in a way you can't describe with words. If you're not talking, we'll know that idea was wrong. When light bounces off an object, the light can be directed by a lens to form an image. A lens in the eye does this and creates an image at the back of the eye, where we have an array of neuron cells that detect the light and send the information on the image to the brain. And it's a similar story for your other sensory cells that pick up other stuff. From there, your brain tries to make sense of the signals, classifying concepts, and trying to build a model of what it's observing. I don't know how that works exactly, how neurons connecting to neurons becomes conscious ideas like white duck jumping. Should probably ask like a brainologist. But for now, let's say our goal is we want the concepts or pictures that we build in our mind to be the same as the world outside. We want to accurately recreate the universe, or at least a part of it, into our brains. We don't want to be wrong. How do we do it? Well, observations are a start. If we want to know what the world is like, looking directly at it is really going to give us the best idea. But at the same time, there's a lot of signals that our sensory cells and brains have trouble with, like certain wavelengths of light and sound, things that are too small, or too far away, or too fast. It can be hard to see an individual part if there's too much stuff going on in the background, if there's too much noise. We can have trouble processing things even when they're right in front of us, like a face with the eyes and mouth upside down. It goes from "Happy Birthday, Mr. President," to "My sister and mother are the same person." The haphazard way our brains and senses evolved to be wired didn't give us perfect accuracy, perception, or memory. But we can use tools to detect things we can't detect. Microscopes for things that are too small, telescopes for things that are too far away. A tool that detects bits of radiation and plays a fun noise. And instead of trying to communicate and remember properties by feel, we can have this thing we call a centimeter. Just count how many centimeters is the same length as this other thing. And we can use whatever standard of comparison we need. And we can try to go slowly and systematically. But some people, after they've had the neurons in a part of their brain die, they may no longer perceive faces. They may not be able to recognize their friends and family, celebrities, or themselves. They can still see eyes and noses and mouths and describe their layout. The signal about the light is still coming in, but the brain no longer classifies visualize this arrangement we call a face. In the end, there may be a lot of things like this, useful classifications about the universe that all of our brains can't conceptualize. But the point is, because those signals coming in from the sensory cells are the only way information can get into the brain, observations are the only way of really knowing what the universe is like. But we can also come to new ideas by playing around with old ones. For example, we call this many 6 and this many 4, but we could also frame them together. Then what do we get? Well, we already have a word for that amount. We call that 10. Split it in half, how do we describe that? Make a sort of square array out of it. Can we describe that quantity? Okay, 5 times 5 equals 25 isn't an observation. It's more a play on our definitions. It's a statement that, according to our naming scheme, 5 times 5 and 25 refer to the same thing. Or let's say that we notice that a parallelogram always has the same area as a square. If the parallelogram always has the same base length and height, and let's say we define the lengths of these sides as A, B, and C, then we can look at the squares and play around. Go bajoop, bajoop, bajoop. Okay, taking what we knew, we could come to a new useful model without having observed it first. I don't think this is how they actually found this equation, but they could have. We can do something like, if everything that we call a flagel is blue, and everything that we call a beaner is a flagel, if that's the information that we know, we should also be able to know that every beaner is blue. Even when they're nonsense words, the new ideas we come to make sense, because it's creating a world in our mind and seeing what we would absolutely have to observe in that world because of the rules that we set. So if we build our rules and definitions and ideas based on observations, we can form new ideas and models that actually describe and match the real world. Okay, this is deduction. But sometimes we can't describe the world with this much certainty. For example, if we start rolling this dice and we put it in with our eyes closed or something, there's no way we could ever know ahead of time what face will turn up when we stop rolling it. But do we know? There are 6 sides, only 6 possibilities for what will be turned up. Perfectly cubed, perfectly balanced. We don't have any reason to think one of the sides is going to turn up more or less than the others. Let's represent the likelihood of each event occurring as being a certain proportion of all the possibilities. Added together, they'll equal 100%. In this case, we think each one has an equal probability of occurring, so they're just 1/6 of 100%. So we might say rolling a 3 has a probability of decimal 167, or of all the things that could happen, rolling a 3 is 16.7% of those possibilities. Or we would expect to see a 3 about 1/6 of the time. This is all we can do. We don't know what's going to happen, so we describe the possibilities. What are the odds of rolling a total of 3 when rolling 2 dice? Each dice has the 6 possibilities. Their outcome is independent of one another, and we can get any combination between them, each combination having an equal probability of occurring. These are all the possible mutually exclusive dice rolls. We've got these 2 ways of rolling a 3. Of 36 possible rolls, there is a 5.6 chance of rolling a 3. Anyways, we've got observation and deduction to form an idea about the world, and they're good, they're pretty good. But this other way we can form an idea is by guessing. Just imagine the way the world is. Great! Why would we do that? I mean, there's a lot of possibilities for things that could be in this mystery box. Only one of those possibilities actually is, so why don't we just look? We can verify the thing that's in there and falsify all the other possibilities. It's because sometimes it's useful not to wait for an observation. Hear thunder? Last time we heard thunder, it rained. Maybe thunder always comes before rain, and it's going to rain. We better put away any horse meat we don't want to get wet. We saw Frank eat these mushrooms. Now he's bleeding out the eyes. These mushrooms must cause bleeding out the eyes. Let's stay away from them. We do it because it seems faster and safer. Our guesses aren't always accurate. In fact, you could say they're often not accurate. For example, the idea that the stars and the sun circle the Earth while the Earth remains stationary. Sure, it looks like they're swirling around us, and it doesn't feel like we're moving, but at the time I think a lot of people were opposed to other ways of modeling the system. Or the idea that you can sweat out toxins through your sweat. I don't know the observation that led to this idea, maybe that you smell after eating certain foods, but it doesn't matter the substance, cyanide, sugar, or water. You can take a certain amount and it's not going to hurt you. It's when you take too much that it starts to cause damage. If we define toxin as a substance that hurts you, then toxin isn't a class of chemical. A toxin is any substance you have too much of. So detoxification would be sort of the recognition of when there's too much of something and excreting it, which doesn't happen at the skin. Small amounts of some stuff does happen to leak out with the sweat, but unlike urine and stool, sweat doesn't have a lot in it. It's almost entirely water. There's no specialized cells at the skin sorting chemicals or making things easier to excrete. Skin cells function mostly as a barrier. How about the idea that there's this god named Thor behind those loud lights in the sky? It's so scary. We better sacrifice another horse. Frank eats everything he sees. It may very well have been something else he ate when we weren't watching. Okay, guessing is fine. It's us wondering about the world. It's not the problem. The problem is assuming that we know, not recognizing that we're guessing. We'll often take the first idea that pops into our head and treat it as though it were true, or treat an idea as true because someone told it to us. We all tend to do it. We all have trouble saying, I don't know. Me, I'm no exception. I'm pretty sure I'm wrong more than I'm right. Probably wrong in this video, but let's see what we can do. Let's call a guess or hypothetical idea about the world a hypothesis. It will either match the world outside or not match the world outside. For us to know whether an idea is true, for us to verify it, we have to observe it directly out there. Turn the made-up idea into an observation. For us to know an idea is false, to falsify it, we have to distinctly see the real world being inconsistent with the hypothesis. But just because we can imagine something doesn't mean we can see it. Some ideas can be unverifiable. For example, the idea that every time we drop this pen, it will fall. It's falsifiable if we see the pen float or go up or something just one time. We'll see that no, the pen doesn't always fall and the hypothesis is wrong. But it's not verifiable. That is, there's nothing we can see that will let us know that this idea is true. Even if every time we've ever seen the pen dropped, it fell, the hypothesis wasn't every time we've seen it. The hypothesis was every time. Every time will always include the next time in the future where we can't observe it, so this specific idea will never be able to be an observation in our mind. Seems like it's stupid, overly strict semantics, but the point of it is we don't ever want to confuse the feeling that we're right with making the observations to actually know something. If the hypothesis was different, every time you drop the pen in this room today, it will fall. The boundaries of the idea have been set and we can see within those boundaries. But a universal idea about the way the world is has no boundaries, and we can never see it entirely. But at the same time, the pen falling seems to be very consistent. We've never seen something else happen. Maybe we just treat it as though it were true, since it's so universally predictive. But remembering in the back of our mind, observations are the way that we know stuff, and we can't literally see all of this idea. Along these same lines, an idea can be unfalsifiable. For example, the idea, a squirrel that looks exactly like this exists somewhere on Earth, let's say. It's verifiable. What would we have to see to know it? Just have to see the squirrel. We'll know it exists. But it's hard to falsify. We would have to see every inch of the planet simultaneously in case it moves around, and see no squirrel in all those places to be able to have observed the absence of the animal, which let's say is impossible, although maybe this is a bad example. If we've never seen one, and we've never seen any signs of it, and we know that animals almost never have two tails, the squirrel is mostly just a made-up idea, we can talk about the low probability of its existence and ignore the idea until there's some sort of observational basis for it. We probably should, but it's just this isn't entirely falsifying the idea. We haven't truly observed the squirrel's absence. Unfalsifiable ideas can be tricky. Even if an idea is unverifiable, if it's falsifiable, you can at least eliminate stuff as you make observations, and the hypotheses that are left are maybe left because they're true. Maybe. With unfalsifiable ideas, we can't eliminate stuff, and the ideas can stick around with little to no observational basis. An idea isn't automatically right or automatically wrong just because we can't see it. Saying it's unverifiable or unfalsifiable is about the disconnect between being able to imagine something and being able to observe it. Okay, some ideas are both unverifiable and unfalsifiable. There's nothing we can see to know that they're true, and there's nothing we can see to know that they're false. For example, since your experience of the world is all controlled by your brain, it's possible your brain is really attached by wires to a computer or something, and all the reality you perceive is fake. Verifiable? Nope. You can even wake up in your vat, wires coming out of your nips, but that could still just be a part of the actual simulation. Falsifiable? Nope. If it's not true, everything would look exactly the same. Okay, it's like a hypothesis about a squirrel that we had no observational basis for, except we think the squirrel is also invisible. It's like a hypothesis about a god who has supreme power who could manipulate the world and our lives, but it's only exerting its will in mysterious ways that are indistinguishable from regular ways. Or a hypothesis that the universe popped into existence 10 seconds ago, and the only reason we didn't notice was because all the atoms and light and our neurons and memory and everything came to be in the exact same shape and position they are now. It may also have happened a year ago, or 6,000 years ago. Again, not automatically right or wrong, it's just we can't see it entirely. Our bodies may be being harvested for energy while we're kept subservient within a simulation, but at least there's pie. To summarize so far, we're wrong a lot, and learning's real hard. Okay, let's say there's this new disease. You get a big lump, but people have been saying that eating carrots can make them smaller, and we want to know if it's true or not true. Basically, we've got two incompatible hypotheses, and we want to know which one matches the world. If we're in a world where carrots do shrink lumps, how would that world look? What observations could we expect to make? The problem with these is that they're hard to verify or falsify, even on an individual level, because of the noise. Kind of like with Frank, just because we observed them eating carrots and then observed some change in their lumps, doesn't mean the carrots are causing it. Could be something else they're eating, or something else going on in their life that's causing this. Even comparing them against somebody who didn't eat carrots might not be much more help, because again, we don't know what else is important, and if carrots make a small effect, it may be lost among the noise. So what else? While we don't know how important the other factors are, maybe if we sample lots and lots of people and put them into 2 different groups, only feeding carrots to one of the groups, maybe all this other stuff will average out. And then if we see a difference in the average lump size between the groups, maybe we can attribute it to the main difference between them, the carrots. It would be nice if we could record or survey these other factors so we can check to see if there's a relationship between those and lump size, and check to see if there's any interactions. You know, maybe carrots only shrink lumps when the person also eats broccoli or something. Or better yet, have both groups eat the same things, have the same lifestyles, and be genetically identical clones so that we can be very sure that any changes we see are from the carrots, although that can be really hard. Okay, 2 groups. Measure lump sizes before, measure again after some amount of time, feeding carrots to one group the whole time but not the other. Let's say these are how much each person's lumps have changed size over the course of the experiment, and these are the average lump size changes of the groups. On average, the carrot eaters' lumps shrunk more or grew by less. So carrots shrunk the lumps, carrots can help? Maybe, but it could also be the noise from all the other stuff. Maybe carrots did nothing, and all these people's lumps were going to shrink and grow for other reasons, and it was just the random way that we put them into the groups that created these results. What we can do to investigate that is to look at every possible combination we could have made with these people, assuming nothing we did mattered. Kind of like what we did with the dice. What we're looking for is the probability of seeing what we saw, assuming carrots do nothing. It's like if we rolled 10 apparently normal dice, and we rolled a 10, we rolled all ones. What are the odds of that happening? Pretty low. There's only one way of rolling a 10, and with 10 dice, there's 60 million combinations we could have got. If we were testing a hypothesis that these are normal dice, you would expect to see rolls in the 30 to 40 range. There's loads and loads of ways of rolling those. Rolling all ones is so unlikely that the hypothesis that these are normal dice is probably wrong. Maybe these are loaded dice, or maybe the dice only have ones on them, or maybe somebody used a camera trick. So same over here. This is the range of possibilities for the differences between the groups, assuming carrots weren't a factor. This would be if we had randomly placed people into the groups like this, and over here if we had randomly put people into the groups like this, and everything in between. And this is how likely each difference was of being rolled. If we see a difference between the groups somewhere over in the middle, it looks like it was just random. But if the difference between the groups was somewhere over in this region somewhere, where under random conditions there's only a 5% chance of seeing it, or better yet, a 1% chance of seeing it, then maybe it wasn't random. Chances are good that there's actually something going on. Where does our experiment fall on here? Here. If carrots did nothing and this was just random, then we shouldn't be that surprised seeing the results that we saw in our study. The hypothesis that it was random is relatively likely. It's not that this difference between the groups is so small that it's just not important. It's about all this variance we're seeing. If our results, instead of looking like this, looked like this, same average difference, but what are the odds of randomly putting everybody whose lumps shrunk in one group and grew in the other? Very low. It's like rolling all ones. Carrots would almost certainly be an important factor. Actually, they look like the only factor. But in our experiment, is it just the other stuff affecting lump size? Or do carrots have some small effect getting drowned out by the noise? We can't tell from the observations we made. And unfortunately, we don't know which hypothesis is true. But there's not a strong reason to think that carrots shrink lumps. Lumps seem to shrink and grow more for other reasons. Or maybe not. 14 people isn't really enough to get a good result. That was a lot of work. Definitely too much work. Can we just trust what other people say about the world? If the all-time greatest physicist says the universe was born some 14 billion years ago after something called the Big Bang, can we just go with that? Maybe, but not if that's all they tell us. We still need to hear the observations behind the idea. A hypothesis doesn't suddenly become true because someone really smart says it. We still need to go through it in our heads as well, even if it's just communicated to us. If we think they've made a mistake, or lied in such a way that we can never find out by looking at their work, you know, they recorded an observation wrong or something, then we would want to see some other people able to make the same observations. And I've never heard of someone who is always right, so even if we trust them, we should be double-checking. It can be hard and full of uncertainty, but this is the process of learning new things, the process of science. Maybe not a proper definition, but it's about building ideas from good and thorough observations, acknowledging what we have and haven't seen, we can and can't see, to try to get what we build in our mind to match the universe we observe. Our ideas are always changing. Even the tools and equations we use to build ideas might change. Entire areas of study might end up being wrong, but the goal is the same.
So hopefully from the video, you were able to see how science is based on observation and reasoning. Also, science is conducted by scientists who are themselves human, just like you. So this means that complete objectivity is not possible. There's inherent bias that leads to reduced objectivity, and it's non-intentional. So how then do we overcome a lack of complete objectivity in interpreting scientific results? The two primary ways in which we overcome this issue of objectivity or lack thereof is through scrutiny and replication. Scrutiny is defined by the process through which science is shared among peers. We call this the peer review process. The cartoon on the left depicts an idea of how science moves through this peer review process. Here you have a scientist that has a manuscript in his hand, shown here. This manuscript details the question the scientist had, the way what his predictions were or hypotheses were, how he was going to test it, how he did test it, the data and the results that were obtained from those tests, and his interpretations, and maybe even a little bit about what it means to the larger science community. Now that's all well and good. Doing science, writing the science up, and the next step in that is to share that with the greater community. And the way in which science does this, or scientists do this, is to submit that work to a peer-reviewed journal. At some point in your educational career, you've probably come across what we call primary literature, the scientific literature, and we call this peer-reviewed because once a manuscript is completed, it's submitted to one of these journals, and then peers, other scientists, as shown here, review and critique that work. Now, in this cartoon, you see that all of these scientists are holding weapons. This shows the scrutiny in the process. It's not a battle to the death, and no one is ever actually physically injured in this process. However, the scrutiny is what allows the work to be as objective and using as much reason as possible. Once a manuscript is submitted, it is critiqued from start to finish by peers, other scientists who are informed and understand that particular area of science. And after thorough review and critique, that manuscript can ultimately, hopefully, be accepted, which is what the billboard in the back says. You've reached the pinnacle, and now that it's accepted, it gets published and is now available for the greater scientific community as well as the lay community to read. Now, it doesn't end there. There's also this idea of replication. So when a scientist writes a manuscript and submits it, it has to be thorough enough, that writing or that manuscript has to be thorough enough that it can be replicated by another lab or another group of scientists independently. So it's important to remember here, or to note, that replication does not mean repetition. It means that the science described there should be an ability for that science to be replicated by an independent source, another lab, under the same conditions and obtain similar or the same results. Now, as shown on the right-hand side of the slide, you see that science, is depicted by replicated experiments. One observation of something is not science. We will revisit these ideas of scrutiny and replication later on in the semester when we look at examples of scientific reports or manuscripts that have not been validated through replication and in fact have been shown to be either falsified and therefore discredited, and they're then removed from the peer review literature base. But before we get there, we need to focus on the process that gets us to the results that are scrutinized and then hopefully replicated. It's something you've probably heard about. It's called the scientific method. The scientific method describes how scientists approach science, but it's important to note that there isn't only one way to conduct science. However, in order to explain and lay fundamental basic ground rules, if you will, for how science is conducted. The scientific method, this kind of process or steps of how science is conducted, has been described for many, many, many years. The scientific method tells us how we need to first identify a problem. We need to then investigate any knowns about that problem or those problems. And from those knowns, form a hypothesis. That hypothesis can then be tested experimentally using independent and dependent variables. From these tests, you'll then collect and analyze data, and then finally draw conclusions. Now, these 6 steps of the scientific method imply a very linear process, moving from one stage to the next, 1, 2, 3, 4, 5, 6. It also implies that there are instant answers and constant answers, and that science is finite. Now, we know that this really isn't how science works. In the previous video, explained this very well, of how falsifiable is really important, as well as verifiable in how we approach hypotheses and understanding or accepting hypotheses. Now, the next video I'm going to show you is a TEDx talk regarding the scientific method. In fact, its title is "The Scientific Method is Crap." Teeman Cook gave this TEDx talk, or TEDx Lancaster, and describes how this linear thought process of how science works is kind of crap, because that's not how science is done. So I want you to sit back and listen and open your mind to think about how science is not only hard to define, but the process itself is more encompassing than how we have defined it up until now for your educational career as this linear, finite scientific method.
The scientific method sucks. Now, by that, I don't mean that science sucks. As a physicist, I believe that science has had countless benefits for humanity. But when I was in 8th grade, I learned about this thing called the scientific method. And since then, I have done science, I have worked with other scientists, and I've taught science to college students, to K through 12 teachers, and to 7th and 8th graders, middle schoolers. And from these experiences, I've come to the conclusion that the scientific method sucks. If it's been a while for you, as it has been for me since middle school, let me run through it real quick for you. First of all, step 1, identify a problem. Step 2, do some research. Step 3, form a hypothesis. Step 4, do an experiment with some independent and dependent variables to test your hypothesis. Step 5, analyze data. Step 6, draw a conclusion. It sounds good, right? It certainly matches what we see on TV and in movies and what we see on the news. Unfortunately, it completely misrepresents what scientists do and what science is all about. And this manifests in 4 main ways. First of all, it's incredibly linear. We start with a problem statement and we end with a conclusion. This implies that science is something that's once and done, fixed for all time. Secondly, it's not very intuitive. How do I choose a problem? What do I do with my conclusion when I'm done? If I have no idea what should or even could happen, how do I come up with a hypothesis? This makes the process intimidating and dangerous. 3, there's a focus on conclusion, reaching the conclusion, on getting a fact. Well, what happens when the information changes? What happens when facts change? How does this process capture that? And finally, the focus on experimentation. Now, don't get me wrong. I'm a big fan of teaching students to control for whatever random variables they can. But there's been a lot of really good science that's been done without being able to control for, well, anything. For a moment, I'd like for you to imagine what budget it would take to create a laboratory here on Earth to study the interior of Jupiter, or to form a star from scratch, or to study a galaxy's development. Do you want your tax dollars devoted toward that? Now, you may be thinking, well, it's probably not that bad. I mean, we've trained generations of scientists using the scientific method, myself included. Surely I'm exaggerating. Well, let me walk through a few statistics with you. 65% of Americans have little to no idea what scientists do on a day-to-day basis. 50% of them, however, have considered it, whatever it is, dangerous. 32% of middle schoolers, of 8th graders, score at or above proficiency in science in 2011. The good news is that's up from 30% in 2009. The bad news is that implies that 68%, 2/3, middle schoolers, score below proficiency. 30% of elementary school teachers feel well prepared to teach science. Now that's compared to 52% who feel well prepared to teach social studies, 66% who feel well prepared to teach mathematics, and 77% who feel well prepared to teach reading and language arts. But here's my favorite statistic of all, the one I find most telling. Of 2,000 parents surveyed in the UK, 50% said that they feared answering their children's questions about science. Questions like, why is the sky blue? And why is the moon out during the daytime? 20%, 1 in 5, said that in response to such questions, they said, no one knows, or made something up. This concerns me. As a culture, as a civilization, we fear science. Why? Well, I believe there are 3 main sources of that. First of all, we're obsessed with right answers. We're obsessed with conclusions. And as we go further and further, we learn more and more stuff. We can't keep track of it all. In addition, the facts, those conclusions, change. Let me give you an example. If you're like me, when you were growing up, there were 9 planets in the solar system. In 2006, one of these things was eliminated. Which brings me to my third point. Why? We don't understand how these decisions get made. We don't understand the thought process behind it. Now, all of these problems possibly don't lie at the feet of the scientific method, but it's not helping. There is, however, a better way. Let me introduce you to the cycle of scientific thinking. This starts with interesting observations. What counts as interesting? Well, if you find yourself asking the question, what happened there? Why did that occur? What's going on? It's probably interesting. In the face of such questions, the human brain does an amazing thing. It tries to come up with an answer, a story, an explanation of what's going on. Now, a lot of people are perfectly happy to have an answer. But scientists, and this is what makes scientists different from other people, scientists want to know if their answer is right. And the way they do that is by saying, well, if my explanation is true, is correct, then I should also see this. They make a prediction. And once you have a prediction, the only thing left to do is to go make observations to see if you were right. And if you are, yay! But if you're not, if you're truly lucky and you got it wrong, then that's going to bring up more questions. Questions that require more explanation, which leads to new predictions, and so on, and so on, and so on. Now, why is this better? Well, first of all, it actually represents what scientists do. In fact, postgraduate education in science is all about teaching people how to take interesting observations, ask pertinent questions, and then develop explanations that lead to observable predictions. This is science. But secondly, and more importantly, it's much more intuitive and much more engaging. The power is in your hands. Once you have an interesting question, do you want to go to the library and read up on other people's answers? Or do you want to skip all that and come up with an answer of your own and see if you can make a prediction and test it? It's up to you. That makes it much less intimidating. From this as well, it becomes much more obvious how explanations change over time. In fact, there are only 3 possible things that can happen to a scientific model. It makes the right predictions, in which case it becomes stronger over time. It makes a few wrong predictions, in which case it is modified over time. Or it makes completely wrong predictions, in which case it will be abandoned over time. The last great thing about this model is that it also illuminates something that's very dear to my heart, the idea that any explanation must be able to be proven false. And to explain this, I want to start with what would it take for me to show that my explanation of a phenomenon is true with a capital T? Well, if it's true, then every prediction it makes should match the observations. Well, how do I check that? I have to check every observation. That's not every observation that I can make with my current budget. That's not every observation that I can make here in this amount of time that I have. It's every observation, everywhere, every when. It's not possible. In order to prove an explanation false, however, all I have to do is find out that it makes the wrong predictions and then make sure that I didn't make a mistake. The way I think of this is to say, if you give me a model that consistently predicts the wrong thing, I can say with certainty your model is wrong. If you give me a model that consistently predicts the right thing, I can say with certainty that your model is not wrong yet. Let me give you an example. In 1781, we found the planet Uranus. But it did this really weird thing. At certain points in its orbit, it was further along than we expected based upon our models, our understanding of gravity. And at other points in its orbit, it hadn't traveled far enough. It was almost as if it was traveling too fast at some points and not fast enough at other points. And astronomers looked at this and they said, it looks a lot like something is pulling it a little bit faster or a little bit slower, depending on where it is in its orbit. Maybe there's a planet out there. Maybe there's something interacting with it gravitationally. And so they did the calculations, they found out where the planet should be, and they pointed their telescopes in the sky at that location. The planet they found we call Neptune today. Now, this was awesome to be able to do this, and there were still discrepancies in Uranus's orbit. So they did calculations. They said, maybe there's another planet out there, a planet X. They did the calculations. They figured out where that planet should be, and they pointed their telescopes into the sky at that point. And they looked, and they found nothing. And this was a problem. And they said, okay, but they continued to look. And eventually, they saw something. And it wasn't where they expected, and it wasn't really the size they expected, but they said, we found something, and it's a planet, and we're going to call that thing Pluto. Fast forward 60 years. Astronomers continued looking, continued taking observations. And another one popped up. Same size, same composition, same location. And then another one. And another one, and another one, and another one. And astronomers said, uh-oh. This is not looking so much like the other planets. This is looking like the asteroid belt, a collection of objects that all share the same orbit, but aren't really planets, not what we think of as planets. And as the evidence, as the observations continued to build, astronomers ended up having to abandon this explanation of Pluto as being a planet. It didn't fit. In the same way, we need to abandon the scientific model. It doesn't fit. Instead, embrace the cycle of scientific thinking. You don't have to be an expert to do science. You don't have to know everything to answer your kids' questions about science. Even if the answer is, I don't know. What do you think? Observe, explain, predict. That's enough. It's good enough. Together, as parents, as educators, and as scientists, we can prepare our kids, our students, our schools, and our country for the challenges of the 21st century and beyond, if we can learn to think differently about science over time. Thank you very much.
The take-home message from this TEDx video is that there is not only one way to do science, and that the process is continuous. We have to open our minds to this type of thinking, and hopefully by the end of the semester, you'll be better at this. So let's recap. The scientific method, it describes how scientists approach science, but there isn't only one way to conduct science. The rules of the scientific method often need bending and adapting, particularly in fields of science involving the unpredictability of natural organisms or humans. We saw this in the examples that Dr. Cook gave regarding the stars and the planets. It's impossible almost to fathom how much it would cost to set up an experiment to generate a new star or to generate a planet. And so there has to be some way that the scientific method can allow us to interpret these ideas. So it's important to know that it's the underlying principles of the scientific method that are much, much more important. And remember, science relies on observable physical evidence as the basis of that understanding. Science is based on both observation and reasoning can be both deductive and inductive. Deductive reasoning applies general principles to predict specific results, while inductive uses specific observations to construct general scientific principles. If we look at an example of deductive reasoning, again, deductive reasoning is the reasoning that uses general principles to make predictions. An example of this is looking at a general principle or premise. In this example, that premise is that monocot flower parts are in multiples of 3. So this statement is what we use as the general principle that we will use to make predictions. So using deductive reasoning, infer from these images whether they are monocots or dicots. Remember, monocot flower parts are in multiples of 3. So here are 4 images of 4 different flowers. And these 4 different flowers can be classified as either monocot or dicot. You can take a moment to jot down some notes. You can pause the video. Great thing about online learning is you can pause the video now and decide which picture represents flowers that are monocots. Once you've decided, we'll go through each flower. The first flower on the left is a monocot. It has, based on this general principle, because it has 3 flower parts, 1, 2, 3. The next image has 1, 2, 3, 4, 5. So by definition of this general principle here, this flower must be a dicot, as it is not a monocot. The third flower is 1, 2, 3, 4, 5, 6 flower parts, so it is therefore a monocot. It's a multiple of 3. The last flower, 1, 2, 3, 4, 5, 6, 7, 8, is therefore not a monocot, but is a dicot. This is deductive reasoning, which is again based upon a general principle that's used to predict specific results. And in this example, those specific results that were predicted were the type of flower, either monocot or dicot, based on that general principle. Syllogism is an argument that's composed of 2 different premises, major and minor, followed by a conclusion. We find this under the overall reasoning type of deductive. Again, it's called syllogism, and it's an argument that's composed of major and minor premises, followed by a conclusion. The example we have here is the general major premise is that all men are mortal. The general minor premise, Socrates is a man. And so we can draw the conclusion based on the major and minor premise that therefore Socrates is mortal. It's important to remember that for any given set of premises, if the conclusion is guaranteed, the argument is valid. However, if the conclusion is not guaranteed, meaning that at least one instance where the conclusion is not followed is observed, the argument is therefore invalid. This was explained in the video that we watched in the first part when they talked about gravity, of how if there was one instance where the conclusion that the pin would drop was not followed, then that would render the argument for gravity as invalid. It's also important to be very careful and not confuse truth with validity. So now let's discuss this. Using the discussion thread on our Canvas course website, you each need to insert at least one idea about the validity of the example given here. When you go to the discussion board on Canvas, you will see that I have started a discussion thread with the example. It's also important that you understand what I mean by idea. An idea here, your idea, needs to be constructive, informative, and relevant. It must be regarding the validity of the above argument. It is not enough to just agree with someone else on the discussion board. However, you can build on other people's ideas if someone has already posted an idea very similar to yours. However, this discussion thread will be counted as half of your assignment 1, and so each person needs to put at least one idea about the validity of this example on the discussion board. Again, it can be your own idea that is more than just an idea. It needs to tell us about your thoughts. Is the argument valid, invalid, truthful? Why or why not? What might be happening? What might be missing? And again, you can reply to someone else's comment or discussion as long as you use these same principles in answering or discussing the example. So the example given is that all students eat pizza. Tyson is a student at UAB. Therefore, Tyson eats pizza. Remember that this discussion board thread is the first of your, will be part of your first assignment, and this will all be clear on the Canvas website. So moving on to inductive reasoning. Inductive reasoning uses specific observations to construct general scientific principles. Okay, inductive reasoning uses observations to construct scientific principles. As an example, we have a list of general observations made here. Poodles have hair, terriers have hair, Dobermans have hair, German Shepherds have hair, Labradors have hair. A general conclusion that can be made from all of these different general observations is that, therefore, all dogs have hair. Using inductive reasoning, can we classify the animals pictured here as dogs? Again, you can pause the video if you would like to take a little bit more time and maybe jot down your thoughts about each one of these images. But moving on, using inductive reasoning, can we classify these animals as dogs using the above observations and conclusions? This first image here has hair. This cute little guy has hair, and it is in fact a dog. This second image here has hair. Not a dog, it's a cat. Third image also has hair. Not a dog, it's a bunny rabbit. This fourth image here does not have hair, but can we classify it as a dog? You might know that it's a dog by looking at it. It's actually a hairless terrier, and it is a dog. But based on these general observations and leading to the general conclusion, that would lead us to believe that this cute little guy is not a dog, and in fact, it is a dog. So you have to be careful making general conclusions and know the limitations of all types of reasoning. Inductive reasoning is a type of reasoning that works from the bottom up. When using inductive reasoning, specific observations can begin to form a pattern. Patterns can be used to formulate tentative hypotheses, and the hypotheses can then be tested. Hopefully you remember that this looks kind of similar to the scientific method that we discussed earlier in part 1 of the lecture. Another example of inductive reasoning is that this bee stung me. It is a hymenopteron. This wasp stung me. It is a hymenopteron. This fire ant stung me. It is a hymenopteron. These are all general observations. The pattern starts to appear that all hymenopterans have stingers or can sting. There is a potential pitfall to this, and that potential pitfall is what we call an inductive leap. If we dig more deeply into hymenopterans, we find that not all hymenopterans have stingers. Some examples include stingless bees and ants, male honeybees, and others. So generalizations might not be correct every time. However, they can be useful. They're particularly useful because as humans, it's in our nature to classify things, to put things in little bins, groups of like things, and make generalizations about them. Doesn't mean it's necessarily the wrong approach. It just means that you have to be careful and not utilize these generalizations as the end-all, be-all definition of something. So our first question is to distinguish between deductive and inductive reasoning. Birds are vertebrate animals that have feathers and reproduce by laying eggs. While on a nature walk, you come across a vertebrate animal that lays eggs but does not have feathers. You conclude that this animal is not a bird. This is an example of, is it A, inductive reasoning, B, deductive reasoning, C, descriptive statistics, or D, reductionism? Again, this is a great time to pause the video and think about your answer. Reread the question if you need to, and then come back and I'll tell you the answer in just a second. So the answer to this question is deductive reasoning. Uses general principles to make predictions. Birds are vertebrates, they have feathers, and they lay eggs. So the animal observed has no feathers, so it must not be a bird. How do we use deductive and inductive reasoning in science? We can think of it as a cyclical process. It works reciprocally. Using inductive reasoning, you build observable measurements through general observations that will allow you to build generalizations that can lead to a hypothesis. The hypothesis can then be tested by making predictions based on the generalizations by the specific experiments that can lead to conclusions. This creates this cyclical process of how it all works together. A few things to know about science. Science is both a body of knowledge as well as a process. It is exciting. It's a way of discovering. Science is useful. It can lead to development of tech. It can treat diseases, deal with all sorts of problems. Science is ongoing. It's continually refining and expanding our knowledge base, always leading to new questions. Science will never be finished. Science is global. It's a global human endeavor. People all over the world participate and contribute to science, and you can too. This is the end of our first week lecture on what is science. Hopefully you have a better understanding of the overall essence of what science is, that it's more than just a bunch of facts. And hopefully you remember to work on your discussion board. Remember, that's through the Canvas website, and there will be a shell waiting for you in the discussion board to place your idea. Part 2 of the assignment of assignment 1 will be posted before Friday.